Wondered what makes a drone fly, a blender whir, or an electric car glide silently down the street? The answer is a marvel of engineering that's all around us, often hidden in plain sight. The electric motor. Today, we're going to demystify this incredible invention and see exactly how it turns electricity into motion. Stick around, because by the end of this video, you'll understand the magic behind one of the most important devices in modern life. Let's start with the basics. At its very core, an electric motor works on a simple principle of physics: electromagnetism. You might remember from science class that when an electric current flows through a wire, it creates a magnetic field around it. And what happens when you bring two magnets close to each other? They either attract or repel. It's this fundamental push and pull that an electric motor cleverly harnesses. To really get it, let's build a simple motor in our minds. Imagine you have a permanent magnet. This is what we call the stator, because it stays stationary. It has a north pole and a south pole, creating a constant magnetic field between them. Now, let's introduce our second key component, the rotor. This is the part that rotates. For a simple motor, the rotor is a loop of wire, also known as an armature. So, we have a stationary magnet and a loop of wire. What happens if we just place the wire loop inside the magnetic field? Nothing. The magic begins when we pass an electric current through that wire loop. As soon as the current flows, the wire loop itself becomes an electromagnet. It suddenly has its own north and south poles. Now we have two sets of magnets, the permanent stator magnet and our new electromagnet, the rotor. And what do magnets do? They interact. The north pole of our wire loop will be repelled by the north pole of the stator magnet and attracted to its south pole. At the same time, the south pole of our wire loop will be repelled by the stator's south pole and attracted to its north. This attraction and repulsion creates a turning force, or torque, on the loop. The loop starts to spin. But wait! There's a problem! Once the loop rotates 180 degrees, its north pole is now next to the stator's south pole, and its south pole is next to the stator's north. The forces of attraction would just hold it there, and the rotation would stop. So, how does a motor keep spinning continuously? This is where the most ingenious part comes in. The commutator. The commutator is a small ring split into two halves, attached to the end of our wire loop. Two stationary contacts, called brushes, press against the These brushes are what deliver the electricity from the power source to the spinning loop. As the loop rotates, the commutator rotates with it. Every time the loop makes a half turn, the two halves of the commutator switch contact with the brushes. What does this switch do? It reverses the direction of the electric current flowing through the loop. And when you reverse the current, you flip the polarity of the electromagnet. The side that was the north pole becomes the south pole, and vice versa. So, just at the moment when the rotation would normally stop, the commutator flips the magnetic field of the rotor. Suddenly, the part of the loop that was attracted is now repelled, and the part that was repelled is now attracted. This gives it another push, forcing it to continue spinning. This happens over and over, twice per rotation, creating a continuous, smooth spinning motion. That's the fundamental principle of a simple DC or direct current motor. You have a stator creating a magnetic field, a rotor that becomes an electromagnet when current flows through it, and a commutator and brush system that cleverly flips the rotor's magnetic polarity every half turn to keep it spinning. It's a constant dance of attraction and repulsion, perfectly timed to create motion. Of course, real-world motors are a bit more complex. This makes the electromagnet much more powerful, generating a stronger torque and a smoother rotation. Some motors also use electromagnets for the stator instead of permanent magnets, which allows for even greater control over the motor's speed and power. Now, let's touch on AC motors, or alternating current motors. These are the types of motors you find in your washing machine or your fan, anything that plugs into a wall outlet. AC motors work on a slightly different but equally fascinating principle. They don't need a commutator or brushes. In an AC motor, the alternating current from your wall socket is already constantly changing direction. In the simplest type of AC motor, the induction motor, this alternating current, is fed into the stator windings. This creates a magnetic field that is not stationary, but is actually rotating. It's like having a magnet that's physically spinning around. Now, inside this rotating magnetic field, we place a simple rotor, often a squirrel cage, made of conductive bars. Here is the cool part. The rotating magnetic field from the stator induces an electric current in the bars of the rotor. Remember our first principle? A current flowing through a wire creates a magnetic field. So, the rotor itself becomes an electromagnet. This newly created magnetic field in the rotor naturally wants to align with the rotating magnetic field of the stator. It's like a dog chasing its own tail. The rotor is constantly chasing the rotating magnetic field, and in doing so, it spins. The genius of the induction motor is its simplicity. There are no brushes or commutators to wear out, which makes them incredibly reliable and low-maintenance. So, to recap the two main types, DC motors use a clever mechanical switch, the commutator, to flip the magnetic field and keep the rotor spinning. AC motors use the naturally alternating current to create a rotating magnetic field that drags the rotor along with it. Both achieve the same goal, turning electricity into motion, but they get there in different ways. The applications are endless. Tiny brushless DC motors provide the precise control needed for computer hard drives and medical equipment. Powerful AC induction motors drive industrial machinery, pumps, and conveyor belts. And the new generation of brushless DC motors are at the heart of the electric vehicle revolution, offering incredible efficiency and power. From the toy car in your childhood to the drone capturing stunning aerial footage, the electric motor is the unsung hero. It's a beautiful application of a fundamental law of nature, a testament to human ingenuity. It quietly and efficiently powers our world in countless ways. So, the next time you hear that familiar hum of a fan or the whir of a kitchen appliance, take a moment to appreciate the incredible electromagnetic dance happening inside. It's not magic, it's physics, harnessed to make our lives easier, more efficient, and more exciting. I hope this has helped you understand the working principle of electric motors. It's a topic that can get very deep, but the core idea is really that elegant and simple. If you found this video helpful, please give it a thumbs up and consider subscribing for more deep dives into the technology that shapes our world. Let me know in the comments what other devices you'd like to see explained. Thanks for watching, and I'll see you in the next one. Have you ever wondered how electricity gets from a power plant miles away all the way to your phone charger? It's a journey that involves some seriously high voltages, but the power that comes out of your wall socket is much, much lower. How is that possible? The unsung hero of this entire process is a device you've probably seen but maybe never really noticed, the electric transformer. Today, we're going to demystify this incredible piece of engineering and see exactly how it works. So, what is a transformer? At its core, a transformer is a device that transfers electrical energy from one circuit to another, usually changing the voltage and current levels in the process. It can either step up the voltage to a higher level or step down the voltage to a lower level. This ability is absolutely crucial for our modern power grid. Think about it. Power is generated at a power station. Then it's stepped up to extremely high voltages for long-distance transmission. Why? Because higher voltage means lower current for the same amount of power, and lower current means less energy lost as heat in the transmission lines. Then, as it gets closer to your home, a series of transformers step the voltage down to a much safer and usable level. Without transformers, our electrical world would be incredibly inefficient and a lot more dangerous. Now, let's get into the nitty-gritty. How does it actually do this? The magic behind the transformer lies in a principle called electromagnetic induction, a discovery we owe to the brilliant scientist Michael Faraday. Found that a changing magnetic field can create or induce an electric current in a nearby conductor. This is the fundamental concept that makes transformers, electric motors, and generators work. To understand this, let's look at the basic structure of a transformer. It consists of three main parts: a primary winding, a secondary winding, and a core. The windings are simply coils of insulated copper wire. The primary winding is connected to the input power source, and the secondary winding is connected to the load that's whatever you're trying to power, like your laptop or TV. Both of these coils are wound around a common core, which is typically made of a ferromagnetic material like laminated soft iron. Here's the step-by-step process. First, an alternating current, or a C, flows through the primary winding. Remember, AC is a current that constantly changes direction, flowing back and forth. This is key. A direct current, or DC, which flows in only one direction, will not work with a standard transformer. Why? Because as the alternating current flows through the primary coil, it generates a magnetic field. Since the current is constantly changing, the magnetic field it creates is also constantly changing. It's growing, shrinking, and flipping its polarity over and over again. This is where the core comes into play. The iron core is designed to be very good at containing and guiding magnetic fields. So, it concentrates this fluctuating magnetic field and channels it from the primary winding through to the secondary winding. Essentially, the core acts like a magnetic highway, ensuring that almost all of the magnetic field created by the primary coil passes through the secondary coil. Now, remember Faraday's law of induction. We have a changing magnetic field passing through the secondary coil. And what happens when a changing magnetic field passes through a coil of wire? It induces a voltage, and therefore a current, in that coil. So, without any physical connection between the primary and secondary coils, we've successfully transferred electrical energy from one to the other, all thanks to the invisible force of magnetism. It's like a wireless power transfer, but on a much larger and more efficient scale. So we've transferred the power, but how do we change the voltage? This is where the genius and simplicity of the transformer design really shine. The ratio of the voltage in the primary coil to the voltage in the secondary coil is determined by a very simple factor: the number of turns or loops in each coil. If you want to step down the voltage, like the transformer in your phone charger does, you design the secondary coil to have fewer turns than the primary coil. For example, if the primary coil has 1,000 turns and the secondary coil has 100 turns, the voltage will be stepped down by a factor of 10. So if you put 120 volts into the primary, you'll get about 12 volts out of the secondary. Conversely, if you want to step up the voltage, like they do at power plants for transmission, you make the secondary coil have more turns than the primary coil. If the secondary coil has 10 times more turns than the primary, the voltage will be stepped up by a factor of 10. Simple, right? The voltage ratio is directly proportional to the turns ratio. But there's a little catch. You can't get something for nothing. This is where the law of conservation of energy comes in. In an ideal transformer with 100% efficiency, the power going in must equal the power coming out. Now, electrical power is calculated by multiplying voltage by current. So, if we step down the voltage, the current must be stepped up by the same factor to keep the power constant. And if we step up the voltage, the current must be stepped down. This inverse relationship is why high-voltage power lines can use thinner wires, because the current is much lower, reducing energy loss and the amount of copper needed. Of course, no transformer is perfectly ideal. In the real world, there are some energy losses. A tiny amount of energy is lost as heat in the copper windings due to their electrical resistance. This is called copper loss. There are also losses in the iron core, known as iron losses or core losses. These are caused by two phenomena, hysteresis and eddy currents. Hysteresis loss is the energy needed to constantly magnetize and demagnetize the core as the AC current switches direction. Eddy currents are small, swirling currents induced within the core itself by the changing magnetic field. To minimize these, transformer cores are built from thin, laminated sheets of a special type of steel with insulating varnish between each layer. This lamination breaks up the path for the eddy currents, significantly reducing them. Despite these small losses, modern transformers are incredibly efficient, often with efficiencies well over 99%. So, let's recap the whole process. One more time. An alternating current flows into the primary coil. This creates a constantly changing magnetic field. The iron core guides this magnetic field to the secondary coil. The changing magnetic field passing through the secondary coil induces an alternating voltage and current in it. The ratio of turns between the two coils determines whether the voltage is stepped up or stepped down, with the current changing inversely. It's a beautiful and elegant application of fundamental physics. From the massive transformers in substations that look like giant metal boxers with cooling fins to the small brick-like ones on your laptop cord and even the tiny ones inside your electronic devices, they all operate on this same principle. They are the silent, steadfast workhorses of our electrical grid, making our daily lives possible by ensuring that power is delivered safely and efficiently wherever it's needed. Next time you plug something in, take a moment to appreciate the incredible journey that electricity has taken to get to you, and the simple yet ingenious device that makes it all possible, the transformer. It is a perfect example of how a deep understanding of physics can be used to build technology that fundamentally shapes our world. Thanks so much for watching. If you found this explanation helpful and want to learn more about the amazing science and engineering that powers our world, don't forget to hit that like button and subscribe to the channel. Let me know in the comments what other topics you'd like to see. See you